Welcome to week 5 of Modern Geometry at Bellevue University. This week is your midterm exam, so your homework is a little bit lighter than normal, and you'll find that the proofs this week are actually a little bit easier because you don't have to write a given or what to prove. I do want to give you a disclaimer that we will not finish completing the proof for Heron's formula in this video. Which has to do with the area of a triangle. We're going to do some of the parts of the proof together, and the rest will be left for you for your homework. This is the first part of our proof for Heron's formula. So again, if you're following along at home, we're using Exploring Advanced Euclidean Geometry with GeoGebra. This is question 4.5.1 from that textbook. And if you're in my class, which is I assume why you're watching this video, because most people don't study modern geometry just for fun. I certainly would not. For this week's work, we are to assume everything in this picture. So typically we would have a given and a what to prove. We're not going to do that here. We're just going to assume everything that you can see in this picture. So I don't have to spend time writing out givens, writing out what I need to prove. I'm just going to go straight to it. Now, for the sake of this video, I'm not going to write down all of the words that I would use for my assignment. I'm going to go through it with you so that you understand and then assume that you can capture that in your own words. So part 1, prove the area of triangle ABC satisfies that the area of ABC is equal to SR, and we are reminded of the semi-perimeter formula for triangle ABC. Keep in mind that A and B and C are not labeled on this figure, but A is the side opposite angle A, so this is A. B is the side opposite angle B, so this is B. And C is the side opposite angle C. So let's go about proving this. Again, I would use more words than I'm going to actually write down, but we're going to go ahead and just get to it. So what I'm going to do is I'm going to start with side A. If I look at side A, I can see that the area of triangle BCI, this triangle, the area of triangle BCI can be found using 1/2 times A times the height, which is R. Now, do I know for certain that that is perpendicular? Yes, because I've been following along in my text and I've read chapter 4, and it's very clear that these are perpendicular segments that are also the radius of the incircle. So I know that the triangle, the area of the yellow triangle, is 1/2 AR. I also know that this green triangle, the area of this triangle, which is triangle ACI, is 1/2 B, and again, R. And similarly, I'm going to look at the blue triangle. So the area of triangle ABI is 1/2 CR. Now I can see based on the picture that if I want the area, let me switch to a different color. If I want the area of triangle ABC, it can certainly be found by adding the area of triangle BCI plus the area of triangle ACI plus the area of triangle ABI. So I'm going to do some replacements. The area of triangle BCI, as we know, is 1/2 AR. The area of triangle ACI is 1/2 BR. And the area of triangle ABI is 1/2 CR. Now, just doing some algebraic manipulations, I can obviously take out the 1/2 and take out the r, and that would give me a plus b plus c, so 1/2 r, a plus b plus c. Now, we're going to go back up here to where the semi-perimeter is equal to 1/2 a plus b plus c. So really, if I just think about changing the order of these to make it a little more clear, this is r times 1/2 instead of 1/2 r. I can replace this with s. So I have just proved that the area of triangle ABC is equal to SR. For the next part of our proof, we're going to take a look at just some equalities that we will need later on. So for the first one, we're going to prove that x plus y plus z is equal to s. Well, if you'll recall, s was 1/2 a plus b plus c. Now, if we know that s is 1/2 a plus b plus c, I can see that a, which again is this side, is x plus y, and b is y plus z, and c is x plus z. And I can see that this would end up with being 1/2 2x plus 2y plus 2z. So it's very clear that if I distributed 1/2, I would get s is equal to x plus y plus z. X plus y equals a. Again, do I need to do any proof on that? No, I don't, because again, I can assume everything given on the picture. So side A is, in fact, remember, if this is x, this over here is also x. So x plus y, I don't have to do any work for those three. So x plus y equals a, y plus z equals b, and x plus z equals c, just given in the picture and the external tangents theorem. Moving on to part B, what we just proved is x plus y plus z is equal to s. So now they're saying prove that x is equal to s minus b. So I'm trying to prove that x is equal to s minus b. So again, is there a lot of work to be done here? Let's take a look at b. b is equal to y plus z. So this could be x plus b is equal to s, and then by subtraction, x equals s minus b. I can do the same exact process for y equals s minus c and z equals s minus a. Next, we are to prove that u plus v is equal to x plus y, and for that we're going to focus our attention on CB. So line CB can be made up of this segment equal to y plus this segment equal to x, and again this is x, so this is x. So CB is the same as y plus x or x plus y. But looking at it a little bit differently, I could also say that CB is equal to, and again we're trying to prove it's equal to u plus v. Well, v is this segment right here. So v plus this segment right here, which is the same as u. So u plus v. Well, CB obviously equals CB, so x plus y is equal to u plus v, because it's the same segment. The second part of part C is actually even easier. We are looking at x plus z plus v, which is, oh, let's not use white there, this segment equal to y plus z plus u, which is this segment, and those are just external tangents and therefore are equal. For the last part of 4.5.2, we're to prove that u is equal to x and v is equal to y. So here we're just going to be utilizing things we've already shown. And that's sort of the beauty of this whole proof, is that we continue to build. So if I take a look at x plus z plus v is equal to y plus z plus u, which is from part C. And if I subtract z from each side, I get x plus v is equal to y plus u. And I also have this equation, and I'm going to subtract x plus y and subtract u plus v, which is this equation just flipped around, so I have x's, y's, u's, v's on the same side. So this gives me v minus y, because the x's would cancel, is equal to y minus v. And therefore I can see that if I add v to each side, I get 2v. If I add y to each side, I get 2y. Dividing by 2, v is equal to y. And then pretty easy from there, if v is equal to y, I can then show that u is equal to x just by substitution. So u plus v equals x plus y. If I replace v with y, I get u plus y equals x plus y. Subtract it, u is equal to x. In 4.5.3, we're asked to show that AV, this segment, is equal to S. So AV, according to my picture, is the same as, and I'm just going to write it in the correct order here, x plus v plus z. In 4.5.2 D, we said that v was equal to y, so by substitution, AV is equal to x plus y plus z. In 4.5.2a, we said x plus y plus z is equal to s, so again by substitution, AV is equal to S. There are 4 more parts of this proof, and you are to complete them on your own. So 4.5.4, we're using similar triangles to prove a ratio. 4.5.5, we're saying 2 angles are equal to 90, and we're concluding 2 similar triangles. We're proving another ratio, and then we're putting together 4.5.1, 4.5.4, and 4.5.6 to prove Heron's formula.